Good morning, welcome to the Queen's Building Energy Lab. This is a new kind of laboratory, and as you can see from the images, it's heavy on the graphics because we're trying to promote the idea of sustainable energy to a whole range of different people. Students, researchers, parents of students, staff, anybody that's got a connection with energy. So over on my left here you can see one of our posters which is all about energy efficiency. And straight in front of me we have another poster which is about renewable energy. Energy efficiency and renewable energy are the two pillars of sustainable energy. And that's the kind of work that we do in this space. As we walk around the lab, you can see here we have a model of a smart home of the future. This is a home that's controlled by an electronic device which shifts the electrical load in the property so that we can smooth the demand that's placed on the electricity grid. In the future, more and more of us are going to have a lot more electrical load in our homes as we shift to electric vehicles, to electric heating systems, and to more and more use of electricity. So what will happen as we all come home from work, plug in our car, switch on the electric cooker, and switch on the electric heating system in the home is an enormous spike of demand on the grid. We need to develop systems that are going to shift that demand in different homes in such a way that we don't notice it as consumers, but the grid sees a smoother demand. Otherwise we'll all be paying for a lot more copper to be buried under the road. That's what this project is about. Over here we can see a large air conditioning teaching unit, which is for students to understand how air conditioning systems work, and also researchers in our architects department to understand how to develop air conditioning systems of the future. Air conditioning loads are projected to increase massively as the world becomes a warmer place and as some of the poorer countries in the world begin to afford to use air conditioning to provide comfortable buildings. Just beyond the air conditioning rig, we see an electrochromic glazing simulator. This is a kind of window coating which is able to dim the windows in a similar way to photochromic lenses in your specs. The difference here is that we can switch the dimming, whereas the photochromic lenses switch automatically. At the moment we're in fully dim mode, but I'm going to turn it up now to fully transparent mode. And if you look back at that in a few minutes, you'll see the window will have become transparent. Over here is a picture of what it's all about. This is the world. This is what we're trying to protect through the use of sustainable energy. At the corner, if you can just see that, is a picture of the sun. More energy hits our globe in 1 hour than we use in a whole year. Our job here is to capture as much of that as possible and not waste it. Here is the poster I mentioned earlier, and over here is the smart kitchen of the future. We have a fridge, washing machine, dishwasher, all the normal things that you would see, including something else that you wouldn't see, which is a controller under here, which is able to shift the load from our electric water heater in the same way that I mentioned earlier. And just beyond the smart kitchen is a window on the world, which in our case is a TV screen or a PC. This allows us to view data which is coming from various experiments around the university. In this case, this is data from a terraced house just behind this building, where we've installed a new energy system which collects solar energy, hides it under the ground behind the house, and then pulls it out using a heat pump for heating the space in the house and the hot water. And then just here is the control system for the smart kitchen, and here is a heat pump demonstrator which we use for the undergraduate teaching in the second year. The heat pump is taking energy from the air, and so this is cool because energy is being taken from the air, pumping it using something similar to a refrigerator pump into this, which is the heat exchanger, and this device here is releasing the energy, which is in the form of warm water, which in your home would be underfloor heating or radiators or your hot water cylinder. Here is a display which shows the students all of the performance figures of the heat pump, so you can see the various temperatures around the system, you can see the flow rates around the system, and you can work out how efficient the heat pump is when it's taking energy from here and putting it here. Welcome to the undergraduate experiment space in the Queen's Building Energy Lab. In this space here, we have all of the various small rigs and one very large rig that undergraduates can use to do their energy experiments as part of their undergraduate studies here. Also, around the room, we've got an energy timeline that starts way back in 1 million BC, when Homo erectus learned to control fire. So that's an energy experiment that our ancestors did. Takes you all the way through many years until we get up to the present day and slightly into the future. Last year, 2015, was the UK's record for wind generation, with 14% of our monthly energy supplied by wind power. And of course, we expect that to be higher into the future. We've got various sayings and phrases and quotations around the Energy Lab, including one of my favourites from Thomas Edison, who said, "We are like tenant farmers chopping down the fence around our house for fuel when we should be using nature's inexhaustible sources of energy, sun, wind and tide." Okay, as we carry on around the lab, you'll see these two rigs which are identical, which are for teaching the students about thermal conductivity. They can see the differences between the conductivity of different metals, measure the conductivity, and try to understand how the heat flow is affected by the different materials. Those are the same, and over here we have a rig which is to teach the students about turbulent heat transfer, and this is a simulation of a cooling tower, the sort of thing you see at power stations. Carrying on around the lab, we have 3 rigs which will be connected together, which are our large heat pump simulator. This is the heat pump unit itself in the middle. This is the source of energy, and this is the sink of energy. Or, this could be the source of energy, and that could be the sink. It just depends how we connect up the 3 units using these pipes on the bottom. So let's start it the first way around. If this is the source of energy, it's what we call an air source. So this is a fan coil unit which is pumping air through a collector, which is collecting heat out of the air. The heat pump is pumping it into this unit, which would then spread the heat through underfloor heating. And you'll be able to stick your hand in here and feel the water getting a little bit warmer, which is in effect underfloor heating, or radiators. If we connect the pipes up the other way around, this can become our source. So in that case, this would be a ground source. This will be taking heat out of the ground, again through the heat pump, pumping it into this, which should now become a fan heater, or it might become warm air ducting through the home. So we can experiment in either way, and we can allow the students or researchers to understand the efficiency of the heat pump in either mode of operation, and we can change things about the system, like for example changing the nature of the fluid in here. So we can experiment with different kinds of soil conditions, we can maybe experiment with different kinds of moisture content in the soil, and so on. Lastly, if you look down, you can see this, which is a model of the building that we're in now. Model of the Queen's Building. It's coloured, it's been produced using a 3D colour printer, and in this model, the colours are connected with the amount of solar energy which is falling on all the different faces of the building. The yellow, in this case, means that these are the best faces to put solar panels on the building. Using this technique, any architect can model any building, and using the data about the sun's passage through the sky around the year, can work out where would be the best place on any building to put solar panels. Welcome to the plant room in the back of DMU's Crime House. This is a very unusual space, partly because it's where DMU mocks up crime scenes for teaching forensic students, but in our case, we use the house to test an innovative energy system. This system is a renewable energy system, and it takes solar energy in the form of electricity, like your normal PV, and also heat from the same panels, and then uses that to both heat the property, the space heating and the hot water, and also generate electricity, which can power the property and also generate a small income for the residents. There are no residents in this house. It's a crime house, so the money goes to the university, and the heat is something that we're using for our experimentation. So over here we can see the solar station, which is taking heat from solar panels via the black pipes you can see going into the loft. The panels are on the outside of the roof, as you'd expect, and the heat is being pumped through this station, out here, and into this unit here, which is a heat exchanger. Then the heat comes from the heat exchanger through these pipes, and either goes underground to the back of the house via these pipes you can see here, which go out of the back of the house, or the heat comes here into this device, which is a heat pump. This is exactly the same type of unit as we have in the energy lab, but this is a small unit, similar size to a domestic boiler, and the heat pump is used to pump heat into either the hot water cylinder, which you can see here, or into underfloor heating, which is downstairs in the front and back rooms in the house. So the rest of the equipment in here is not actually to do with heating, it's to do with our research. This little device up here is controlling the heating system, but it's also recording data about all of the different temperatures around the system and the flow rates of the various bits of fluid flowing through the pipes. This allows us to calculate the heat flow around the system and the efficiency of the system. Over here we have a computer which we're using to collect all of the data about the temperatures in the thermal store, which is outside the back of the house. The computer takes its data from this device here, which is a data acquisition system, which is collecting data from thermocouples in the Earth Energy Bank, the store, and also data from these brown wires here, which is temperature data from the solar panels. Okay, so as well as heat, which we talked about so far, the solar panels are collecting electrical energy. That comes through this device here, which is the so-called multi-gate, and the electrical energy comes from two types of panel. Firstly, most of the panels collect heat as well, as I've just explained, but one of the 8 panels only collects electricity. That way we can compare what happens to a solar panel that you take heat out of from the solar panel that you don't take heat out of. That comparison is done via this computer system here, and then underneath here we have submeters which are allowing us to collect the electrical data to do with the energy consumption of the heat pump, the energy consumption of the solar station, and the small amounts of energy that are consumed by the computer and the data acquisition system. We need to be able to subtract the electrical energy that we have used to drive the system from the electrical energy that the system itself has captured to be able to work out the efficiency. Thank you. Okay.